Good afternoon, my name is Adrián Ruiz and the title of my presentation is Use of a solvable pair of variational C-infinity symmetries to reduce the order of Euler-Lagrange equations. This is a joint work with Concepción Muriel from the University of Cádiz and with Professor Peter Olver from the University of Minnesota. So the outline of the presentation is going to be as follows. First, I will introduce the notion of variational symmetries and how we can use them to reduce the order of Euler-Lagrange equations associated to variational problems. After that, I will introduce the notion of variational C-infinity symmetries and how this concept also leads to order reduction of Euler-Lagrange equations. After that, I will introduce the concept of solvable pair of variational C-infinity symmetries, and finally I will conclude the presentation with an example of application. So let us start with the notion of variational symmetries. So throughout this presentation, M will denote an open set with coordinates x and u, and x will denote an independent variable and u will act as the dependent variable. Also, M upper n will denote the nth order jet space which has coordinates x, u, u1 up to un, where here u sub I denotes the derivative of order I of u with respect to x. Also, I'm going to consider an nth order variational problem written in this form, where here omega is an open set of the space of the independent variable and L is called the Lagrangian of the variational problem, which is a smooth function defined on the nth order jet space. So it is well known that the extremals of the variational problem satisfy the Euler-Lagrange equation, which can be constructed by applying the Euler operator to the Lagrangian L in such a way that if the variational problem is of order nth, then the Euler-Lagrange equation becomes a 2nth order ordinary differential equation. So if we consider now a smooth vector field defined on the base space M, we will say that this vector field is a variational symmetry or a nether symmetry of the variational problem if this infinitesimal condition is satisfied, where here view upper n denotes the standard prolongation of the vector field view to the nth order jet space, and dx denotes the total derivative operator with respect to x. So the importance of variational symmetry is because they produce order reduction for the Euler-Lagrange equation associated to variational problems in such a way that if a variational problem admits a variational symmetry, then the order of the Euler-Lagrange equation can be reduced by 2, and also the general solution of the original Euler-Lagrange equation can be reconstructed by a quadrature from the solution of the corresponding reduced Euler-Lagrange equations. So now we are going to introduce the notion of variational C-infinity symmetries, which is a generalization of the concept of variational symmetries. So we are going to consider again an nth order variational problem written in this form, where here again L will denote the Lagrangian and the corresponding Euler-Lagrange equation, which, as I said before, turns out to be a 2nth order ordinary differential equation. So now we are going to consider a smooth vector field view defined on the base space M, and also a smooth function lambda defined on the first order jet space. So the function lambda depends on x, u, and u1. So the notion of variational C-infinity symmetries is based on a new way of prolonging vector field called the lambda prolongation of a vector field. So the infinite lambda prolongation of a vector field view is the vector field defined in this way, where the coordinates satisfy this formula here below. So as we can observe, if we set a lambda equals 0, then this prolongation corresponds to the standard prolongation of vector fields. Also, a remark here is that when this vector field acts on any differential function, then we only need a finite number of terms in this sum. So therefore, this formal expression is well defined. So this lambda prolongation of vector fields motivates the following definition. We say that a pair view lambda is a variational C-infinity symmetry, or also called a variational lambda symmetry, if this infinitesimal condition is satisfied. Where here, if we set up lambda equals 0, then we recover again the condition of standard variational symmetry. And the importance of variational C-infinity symmetries lies in the possibility of reducing the order of Euler-Lagrange equation, as stated in this theorem. So if we have a variational problem of order n admitting a variational C-infinity symmetry, then we are able to reduce the order of the Euler-Lagrange equation by 2. But in this case, we lost a one-parameter family of solution in the reconstruction process. So this means that we can also recover a 2n minus 1 parameter family of solution of the original Euler-Lagrange equation from the corresponding solution of the reduced Euler-Lagrange equation. And another difference from the standard variational symmetry is that this reconstruction problem is made by solving a first order equation, not just by quadrature as in the case of standard variational symmetries. So many papers in the literature have proved that variational symmetries and variational C-infinity symmetries are useful for finding exact solution to Euler-Lagrange equation. So now we center our attention in how we could use two variational C-infinity symmetries in order to perform order reduction of Euler-Lagrange equation by using these two variational C-infinity symmetries. So for that we consider again an nth order variational problem written in this form. L again is the Lagrangian function, and we consider its corresponding Euler-Lagrange equation. And now we assume that the variational problem admits two variational C-infinity symmetries given by these two pairs, where here remember that V1 and V2 are smooth functions defined on the base space M, and lambda 1 and lambda 2 are two smooth functions which depend on x, u, and u1. So in order to use these two variational symmetries to reduce successively the order of the Euler-Lagrange equation, we have defined the notion of solvable pair of variational C-infinity symmetries. So we say that these two variational C-infinity symmetries form a solvable pair if the corresponding lambda prolongation of the vector fields V1 and V2 are pointwise linearly independent on the corresponding jet space of infinite order, and also the corresponding infinite lambda prolongation they satisfy this commutator relation, which means that these lambda prolonged vector fields satisfies a solvable condition, where here the function h depends or can depend on x and u. So in this situation, we are able to prove the next theorem. If an nth order variational problem admits a solvable pair of variational C-infinity symmetries, then we can successively reduce the order of the associated Euler-Lagrange equation by 4. And also, it is possible to reconstruct a 2n minus 2 parameter family of solution of the original Euler-Lagrange equation by solving successively two first-order equations. So now I would like to illustrate how this method works in practice with an example of application. So for that, I'm going to consider a second-order variational problem where the Lagrangian is given by this expression here. So it can be checked that the Euler-Lagrange equation associated to the variational problems becomes this complicated fourth-order ordinary differential equation. And also, it can be checked that this Euler-Lagrange equation does not admit Lie point symmetries, which implies that the variational problem does not admit standard variational symmetries, because the variational symmetries are inherited as Lie point symmetries of the corresponding Euler-Lagrange equation. So here, in this example, at first sight, we do not have any standard methods to find some exact solution of this fourth-order Euler-Lagrange equation. So now we are going to apply our method based on the existence of two variational C-infinity symmetries that form a solvable pair. So in this case, it can be checked that two variational C-infinity symmetries of the Euler-Lagrange of the variational problem are these two pairs, and also it can be checked that they form a solvable pair. So the corresponding lambda prolongation satisfies the solvable condition I showed you before. So now we can start the method of successively reduce the order of the Euler-Lagrange equation by using this solvable pair of variational C-infinity symmetries. So first, we are going to perform an order reduction of the original Euler-Lagrange equation by 2 by using the first variational C-infinity symmetries. So for that, we consider a complex set of second-order invariants for the lambda prolongation of the vector fields, this one. So it can be checked that second-order invariant for these vector fields are these two functions, w and w1. So it can be checked that the original Lagrangian can be written in terms of the invariance of the lambda prolongation of the vector fields in such a way that this reduced Lagrangian is obtained. And the Euler-Lagrange equation associated to this reduced Lagrangian takes the form of this second-order ordinary differential equation. So here, an important remark is that this second-order ordinary differential equation does not admit Lie point symmetries neither, which also means that the reduced Lagrangian does not admit variational symmetries. So here, again, it seems difficult to solve this second-order Euler-Lagrange equation by means of standard methods. So in order to avoid this difficulty, we are going to use the second variational C-infinity symmetries that formed the solvable pair. So for that, it can be checked that the solvability condition implies that the second variational C-infinity symmetry provides these new variational C-infinity symmetries for the reduced variational problem. So here we can apply again the computation of the invariance of the corresponding lambda prolongation of the vector fields. So a first order invariant takes this form, and it can be checked that the first order reduced Lagrangian that I showed to you previously can be expressed in terms of the invariant of this lambda prolongation in such a way that a new reduced Lagrangian is obtained. So as we can see here, this new reduced Lagrangian is of zero order. So its associated Euler-Lagrange equation becomes an algebraic equation which has this form. So now we are going to show how to reconstruct the solution for the corresponding reduced Lagrangian. So from this algebraic equation, we have the solution z equal 1. It's just an algebraic equation. So in order to perform the first reconstruction, we consider the expression of the invariant z. So if we remember, z was equal to this expression. So here we have a first order equation that we can solve in order to find a one-parameter family of solution for the second order Euler-Lagrange equation, where here C1 is an integration constant. So here again we can use the expression of the invariant W, which was equal to this expression here, and we obtain again a first order equation that we can solve in order to reconstruct a two-parameter family of solution for the original Euler-Lagrange equation. So it can be checked that by solving this first order equation, we obtain the following expression for the function u. And also it can be checked here that this function u, which takes this form written here, satisfies the original fourth order Euler-Lagrange equation that we have showed to you before, and which was apparently very difficult to find some exact solution. So I conclude my presentation here. Thank you very much for your attention.